Hi, welcome to lecture 7, and we will talk about particle propagation today as promised. Today is also a good day since after suffering through substantial formalism developments, we are ready to harvest some cool physics facts. So first let's have a look at propagation of a free particle, which means that it's just following the equation of motion of the free um, free Klein-Gordon equation, since we'll be talking about scalar particles. Now we can ask the question, what is the probability to find a particle at a space-time point x, given that it was originated or generated at a space-time point y? So the structure we have is the field operator creates a particle at space-time point y from the vacuum. This is the only way we know how to get particles. And then the field operator at space-time point x annihilates it again to leave us with a vacuum state, to have a beginning and the end point of the particle word line. And the structure, we write it like this. We have again vacuum, particle creation, particle annihilation, again vacuum, and this whole object here, we can call it actually amplitude, but we will come to it later. And this is in principle the simplest process that we can evaluate in quantum field theory. We will actually talk a lot about amplitudes, what happens from initial and final states. And the simplest thing what can happen is just that a particle just moves through space, and follows the free equation of motion. We can put in, as before, as in the last lecture, actually with the commutators, we can just put in the field definitions here. And we see that the only term that survives is this A dagger term with the creation operator hitting the vacuum, creating a particle, and annihilating a particle, and then this is a combination that is non-zero. The other combinations vanish. We can evaluate it by, for example, pulling this operator onto the other side using the commutator, and then we will get rid of one of the state where the annihilation operator hits the vacuum, and the remaining delta function will get rid of the Q integration. So we are left only with this expression here. The integral over e to the negative I p x minus y. It looks like quite a quite harmless function, but it has a lot of structure in it. And we will call this propagator dx minus y. Yeah, because the argument is x minus y, and those are the four vectors, x and y. Now for space-like separations, we said space-like is where events are not in each other's light cone and cannot influence each other. We have, as we will show a little bit later in greater detail, but we have an exponential decay of the propagating function here. We can rewrite it and show that we just have e to the minus m that multiplies x minus y. This we can show that by picking explicitly t equals t prime and having a space-like vector separation and going through the calculations. But we see that the propagator decays exponentially outside of the light cone. Yeah, if we have the light cone like this, as we remember, and 2 points like this, they're separated in space-like manner. The propagator outside of the light cone decays, but it's non-zero. This is a bit concerning. So why do we have this kind of quantum leak outside of the light cone? It's suppressed by the mass. So the range of the leak is 1 on mass. As you remember, this is the Compton wavelength of the particle, where you have some quantum probability that the particle might go out of the light cone. But that still, the commutator vanishes for space-like separations for field operators. So how to reconcile this? We can write phi and x and phi y as before, just as it is an identity that we can write it as dx minus y minus dy minus x. And this actually will show us that since, as a simple example where the times are different, but times are the same, but the spatial components are different, so this is an absolutely clearly space-like separation, we will see that those two functions exactly cancel each other to give us 0. So there's an interesting symmetry or structure in this theory, which preserves causality, even though the propagators on the quantum level seem to leak out of the light cone. Yeah, so what does it mean physically? Physically, it means that there's no way of actually time ordering events when they're space-like separated, because there is no causal structure there. So if a particle travels from x to y, it could be as well parts traveling from y to x in a space-like trajectory. There is no real causal way of phrasing or expressing this statement or this physical process. Now, that seems to be encoded in this canceling of those two propagation probabilities. But now, what does it really mean in physics? We are about to make a first big prediction from quantum field theory, so get ready. To see that explicitly, we have to go again through some more formalism, and we have to consider a complex field. Let me first call the field psi to distinguish it from phi. It's a scalar field, but now its complex conjugate is not a field itself. So it has 2 degrees of freedom. Yeah. And the main thing that is new, what we can now do, is that you can multiply the field psi by a complex phase unit, one complex number, e to the I theta, which theta is just an angular variable. And it is a complex rotation, essentially, of psi in the complex plane, but it leaves the Lagrangian, which is given by this expression, as you remember, invariant. Since obviously, since theta doesn't depend on space and time, the derivatives don't act on it. So this term where you have the derivatives multiplying each other multiplying each other with the complex conjugation, this term drops out because in this complex conjugation you get e to the minus I theta. This cancels. And also psi times psi star is essentially the absolute value of psi squared, where the unit 1 phase rotation is irrelevant, drops out. So this is good. And since we have a symmetry of a Lagrangian, remember the Noether theorem, we have a conserved current here. This is defined like this: dl Lagrangian divided by d mu psi times the variation of psi, and then it is conserved in this 4 current way. Now we can compute what is actually the conserved current, and dl d mu psi gives us d mu psi star, and the variation of psi is just psi times I theta. We can Taylor expand e to the I theta as 1 plus I theta for small theta. So the variation is just given by this I theta term, multiplying psi. So here we have psi I theta from this variation. And next term is dl by d mu psi. So because we have 2 degrees of freedom, psi and psi star, we have to also take the derivative with respect to psi star, or derivative of psi star. And that gives us the d mu psi term times the variation of psi star, which is psi star times negative I theta. Because here, e to the I theta star was equal to e to the minus I theta equals to I minus I theta. So the variation is minus I theta. Okay, having this, we gather terms. The theta is constant, so we don't really care about it. So the conserved current is really this one. This is also part of homework sheet 1. And let's just recap how we do it. To prove that it's conserved, we contract the current with the derivative operator, and we have to apply now the product rule of d mu to each of the terms. Apply the product rule. First, derivative of d mu psi is d mu psi star. Okay, there's let me check. So if this is yeah, this is correct, but this star actually, I apologize, this star, we have a live update. This star has to live on this derivative operator. Yes, the bracket was misplaced. Apologize for that. All right, so we have this bit where we have the derivative now acts on this d mu psi star. So we have d mu psi star, and psi is unaffected. And the next term is d mu star, and then the derivative acts on psi. So we have d mu psi star. Now minus the same story on the other terms. Where two derivatives hit psi, and one where each derivative hits psi and psi star. Those are symmetric and they cancel and have negative sign. This they don't cancel at first sight, but we can remember that we have actually equations of motion and the field satisfies them. So we can take the equation of motion, which is this, d mu minus m squared on psi is equal to 0. We can bring this to the other side, and then we know that d mu psi is equal to m squared psi, and the same with psi star is equal to m squared psi star. Substituting those terms here gives us just m squared terms up front, but then psi star minus psi star just cancels and we get 0. That's good. This is what we wanted. So the 4 current is equal to 0, and that means that if we take this volume integral over the entire expression, we can show that the divergence of the spatial current, since it's a total derivative that is integrated over the entire volume of space, is a boundary term that vanishes. So this is 0. And we can set to 0 the time derivative, the integral over the time derivative of the 0 component of the current. That means that this expression here, the integral over the 0 component of the current, is a conserved quantity. And then we can write out explicitly what the conserved quantity is. This is psi dot star minus psi dot psi star. If you remember the definition of the canonical momentum, this is just psi times pi minus pi star psi star. So this is the definition, and we call this a charge. This is conserved value for this field, and we can really think of it as an electric charge that is carried by this field. Doesn't matter that we don't really talk about electrons. This is a complex field, a scalar field, but it still can carry charge that behaves for our purposes exactly like electrical charge. Now, the field operators can be decomposed as well for this field. Here, we remember we need independent coefficients for those that multiply the exponential functions for the field to be complex. And like we call them now B and C instead of, not to confuse them with A and A dagger. And they mutually, or like each of them in pairs, have the same commutation relations as A and A dagger, only that now we have B and B dagger and C dagger, giving us the delta function, which is the 1 in function space. And the two B's, two C's, B and C, or B and C dagger, they all commute. So their commutators are all equal to 0 for all momenta. Now the field commutator for psi and psi dagger can be also rewritten just by plugging in and explicitly writing out in terms of those two propagator functions. The commutator is equal to the difference in propagators where we exchange the starting and final point. And there's quite an interesting meaning here. So what does it mean? So they have x minus y. To write this, it has to be written as a particle that is, or yeah, a particle created from the vacuum at point y, and then annihilated at point x. But now, since we have particle and particles and antiparticles in the game, we really have to make sure that there's a particle created and the particle annihilated. So the field, mathematically, the field operators have to be related by complex conjugation, and charge conjugation. So this is um, to make sure that you don't create a particle and annihilate an antiparticle. That would be that would not conserve the charge, such a process. So consequently, if we have yx flipped, we actually produce then an antiparticle at point x and annihilate this antiparticle at point y. Yeah, so to create particles, we need the dagger operators here. To create antiparticles, we use the operators without dagger, and to annihilate antiparticles, then we use the opposite operators. Yeah, so now we really have to distinguish between creation and annihilation of particles such that the charge is conserved. Yeah, so we have in particular, a particle going from x to y, or an antiparticle going from y to x. Let us now again go through this calculation a little bit more carefully. What happens at space-like separations, and this can be done by setting the time to be equal and just calling the difference vector x minus y r. This is the construction we get with the light cone. We have x and y separated by distance r. They are outside the light cone. They should be not causally connected. Now let's first compute this copropagator dr. This is x minus y. Remember, x spatially. T minus t prime is 0, and the x minus y is r. That's why we call it d of r. We write it we just write it out, the definition of it. We know what it is. Now remember, this is a scalar product in the normal Euclidean space. So this is magnitude p times magnitude r times cos theta, which is the angle in between them. This measure can now be written as integral over p. P squared dr is the integral over the magnitude. Then we have d phi. There's no phi dependence. Integrating d phi from 0 to 2 pi will just give us 2 pi. And the integral over d cos theta will play a role. So first we do the integral over phi because it's easy. This gives us 2 pi. The integral over cos theta gives us two terms. Like this is the EIPR on IPR. Since we integrate from minus 1 to 1, we get two contributions. The one evaluated at 1 and one evaluated at minus 1. And now we just have to evaluate this p integral. Okay, but for this we have to go to the complex plane. Think of the complex function analysis, and we notice that this function here has actually branch cuts at starting at plus I m and minus I m. If I plug in I m here and larger imaginary values than m squared, and then I will get then I will get first I get a divergence here when p is equal to im, and then there's a flip in the sign. So such a behavior is called a branch cut in the function, and so essentially it's like a collection of poles. So we can rewrite this by wrapping the integration contour in the complex plane around the branch cut. So if the branch cut is at plus im, we can wrap the contour, for example, like here's the picture, sorry. There's the real part of P. This is the imaginary part of P up there. They're like the M and minus M values, and up here is the branch cut. So we can wrap the integration contour about the upper branch cut, setting the integration or the integration variable to be rho that we identify with negative IP. Having that, we have real prefactor, and then we have this integral here, e to the negative rho r dr times rho width divided by the square root. Looks complicated, and we have to integrate from m to infinity because we integrate essentially along the, summing up the divergences along this branch cut here. So we could evaluate it explicitly to have a complicated function, but noticing that r, if we assume r is very large, then we can use the saddle point approximation, and then we get some prefactor multiplying it, this function here at its minimum, and the minimum is at e to the negative mr. Yeah, at larger values of rho, this function will be even more suppressed. So the integral is dominated by negative EIMR, negative mr. Yeah, so this is what we already used before, but now you have proven it. And for the other x minus y propagator, this d minus r propagator, we can choose, instead of negative I p, we can choose the variable to be ip, and close the contour around the lower branch cut, summing up now from this negative m to negative infinity. And we can just get the same integrals. If you rewrite this just with the appropriate substitutions, we use the saddle point approximation on the second integral, just closing the other contour, and because frankly the other prescription would not converge. So the only choice we have once we've done this substitution is to close the contour around that branch cut. So it's not really our choice; it's the only choice to make it convergent. And we get also the same function, negative e to the negative mr. So overall, we have this psi dagger commutator for a space-like separation, gives us this difference of these two functions, and since we have proven that they are identical functions and they're subtracted, that gives us 0. Now, the r is formally a particle going from x to y, and the other d minus r is an antiparticle going from y to x. So, because we have to write them out, okay, here is actually the vacuum, creation and annihilation operators. Let's be consistent. Yes. We have creation and annihilation from the vacuum state, and this is particle propagation, while this is an antiparticle propagation. This is what I meant by showing you this picture here, yeah? So these two expressions here are particle going this way or antiparticle going this way, and they mathematically just cancel out the structure, yeah? I mean, it is actually nonsense to say that the antiparticle is really traveling back in time, because if you have a space-like separation, there is no causal, the motion is not causal. So we can't really arrange events in a meaningful way in time, but we see mathematically that the antiparticles formally moving in the opposite direction cancel contributions from the particles. That prevents even that this leak on the quantum level, the leaking out of the light cone, to give us any means to communicate information, and that is implemented in this fact that the total commutator here of the fields actually vanishes. So the big point here is again that we really need antiparticles to preserve causality. In the other case, where we had the same, very similar expression for the real field, the connection was not that obvious, because for the real field, the particle and the antiparticle are the same. But that's why we went through the exercise and calculating this business for the complex field, to explicitly see that we have the charge conjugated particle that changed the order of propagation, and that means that to preserve causality in a general theory, each particle that carries charge needs a particle that carries the opposite charge. This is a beautiful result by quantum field theory and predicts antiparticles. They were actually the antiparticles, or the positron, the antiparticle of the electron, was predicted in 1928 by Paul Dirac. And it was discovered, but the funny thing is it was discovered even before the prediction in 1925, but not really taken for real, not taken seriously. The person who conducted the experiments was thinking that it makes sense and didn't really interpret or didn't really publish the data in a meaningful way to claim a new particle discovery. Then, after Dirac predicted the existence, the existence of the positron, it was found and now correctly interpreted in 1932, which led to a Nobel Prize in 1936, but very rapidly. So it's interesting that actually this experimental discovery here without the theoretical kind of interpretation was discarded, and only after the theoretical prediction and understanding the proper data was interpreted. Well, now let's understand a little better time relations and introduce the so-called Feynman propagator, named after Richard Feynman. And the propagator is time-ordered product of the fields inside the between the vacuum states. Yeah. So this is now the time ordering operator that does the following. So if the x naught, so the time component of x is larger than y, it picks the propagator that is x minus y. If the time component y is bigger than x, yeah, so the time component x naught minus y naught would be negative, it flips the sign here and gives us the dy minus x propagator. So this operator t is called the time ordering operator. And it places all operators evaluated at later time to the left. So yeah, if x is later, it goes to the left. If y is later, y goes to the left. We can write this Feynman propagator as a four momentum integral, which is quite useful. Yeah, we have now, for the first time, fully obviously Lorentz invariant measure. We integrate over the four momenta d4p. There's a 2 pi to the 4 in the denominator. There's this exponential function, negative ip x minus y, and here's I divided by p squared minus m squared, where the p squared is the four momentum squared. Note that it's not necessarily equals to m squared, because this is now a four momentum dummy integral variable integrated over all values. Now, we also see that this expression actually has poles when p squared equals to m squared. And we can evaluate it partially if we do the integral over p naught. Over in the complex plane, again, we have to use complex analysis and the residual theorem, which we discussed or refreshed recently. We can take the complex plane of the variable p naught, where p naught will have an imaginary part and a real part, and we can go through the contour, and we know that it has poles where p squared is equal to m squared, which is equivalent to e being equal to plus or negative square root of p squared, of momentum p, spatial momentum p squared plus m squared. So this is when e is equal to plus square root, we have a pole here, and then we have another pole here. So what we want to do is to take the integration contour along this line, avoid these poles. See, this one we will avoid in the lower half plane, and this one we will just jump over in the upper half plane and go like this. Let's just prove one thing first, is that p squared minus m squared can be just written as 1 divided by p naught minus e times p naught plus e, right? P, remember, is just p spatial p squared plus p squared plus m squared. And this is then the total momentum p squared and the negative m squared. So it's just reshuffling of terms, But writing these terms in such a way shows us that there are poles at EP, P naught equals to negative equals to EP, or P naught equals to negative EP, as we showed already here. And we can find the residue of the poles, that it is equal to plus minus 1 divided by E, 1 divided by 2EP, with a positive or negative sign depending on the sign of the pole. So let's look at different options here. First, we can check the option that x naught is bigger than y naught. And now we can close the contour in the lower half plane here, option 1. We go and integrate along this contour, closing it here. And so now P naught at infinity goes to negative I infinity here and here. And when we send P naught negative I infinity, this expression, given that this difference is positive, goes to 0, because then we get in e to the minus infinity, this goes to 0. So we can, in this half plane, in the lower half plane, we can just do whatever we want essentially. It doesn't affect the integral. We can close the contour, and just having the closed contour, we can use the residue theorem and get the value of the integral by just summing the poles. Or we sum the residue at the poles, which is then negative 2 pi I divided by 2EP, where the negative sign comes from the clockwise contour. Remember, anti-clockwise contour was positively defined. Clockwise gives you a negative sign. So plugging it in this expression, then P naught is also replaced by residue value. And then we see that this combination is just the four momentum product of P and x minus y. And this one we simplify just to have 1 on 2 EP here. Beautiful. So this is just the expression for the propagator from x to y. This is good. So this is ticked off. If x is bigger, x naught bigger than y naught, we recover the time ordered prescription propagator dx minus y. In the other case, when y naught bigger x naught, we have to close the contour in the upper half plane, right? Sending p naught to positive I infinity. Since this is a negative number, then this will go to e to the negative infinity if p naught goes to positive I infinity, right? So this goes to 0, and we go through the contour in this way, and again close it counterclockwise. Now we have a no negative sign that comes from the orientation of the contour, and we get this expression here, analogously to the above. Now we see that we can actually flip the sign under the integral of p to get a negative sign. Yeah? Here we have a minus ip, and this again combines to the ip y minus x with the Lorentz invariant measure up front, and this is the propagator y minus x. So depending on the ordering of y and x, we get different the dyx or gxy. This is what we needed to actually have the time ordered propagator here. That is, this was how we defined the Feynman propagator. Finally, there is a little trick which we can use by rewriting the Feynman propagator with a I epsilon in the denominator, where epsilon is positive and infinitesimal. It lifts this pole up in the upper half plane, and this lowers this pole in the lower half plane, so we don't really need to deform the contours and just can do a single integral, and it will be closed in the upper or lower half plane depending on the causality or of the order of xy, the sign of x naught minus y naught. In the convergent part will give us the propagator that has the proper time ordering. So this is a very useful expression. Now, finally, to comment on another issue is that we have actually the propagator that is also a Green's function of the Klein-Gordon derivative operator. Just remember what the Green's function is. It is for linear differential operators. We can have equations where uh, for example, defined by the linear differential operator L acting on a function u gives us some function f. Now, if we have the Green's function for this operator L, the Green's function is defined by the fact that if we have the product of the Green's function and L under the integral, that we get delta function. So taking the integral now for a one-dimensional example, L times the Green's function times the u function, since we have this expression given as the delta function, we get after integration just the u function back here. But we only worked on the left-hand side and used the definition of the Green's function. And on the right-hand side, we have the Green's function multiplying f and taking the integral. And that means, again, since we know that this expression is a calculable expression and is equal to what u here, we can find solutions for this differential equation by use of the Green's function. So taking essentially a convolution of the Green's function with a inhomogeneity here, where the Green function is now the integration kernel, gives us a way to generate solutions or to solve this kind of linear differential equations. This can be a useful feature of the for solving problems. And let's just convince ourselves that the propagator actually has this property. Here we have the Klein-Gordon equation, which is d mu contraction minus m squared, which can be written as dt squared minus the spatial integrals, spatial derivative squared minus m squared. Let's apply it to the Feynman propagator, pull the derivatives to the integral, and now since we have this e to the I p x minus y term here, the spatial derivative gives us an e squared, 2 times spatial, the time derivatives gives us 2e squared. Then the 2 times the spatial derivatives gives us dot product of p squared. The every time an I comes down, so we get like I squared, so we get the negative minus sign here. So this is actually minus p squared, which is the dummy variable p4 momentum that we integrate over. And the m squared is just a constant, so it's multiplying the thing here. But now observe that we actually have this expression and this expression that cancel under the integral up to minus sign, minus 1 comes out. So we have minus I, the I here comes out, times this expression, which is a 4 momentum integral of the e to the I p x minus y with 2 pi to the 4 in the denominator, which is just a definition of the 4-dimensional delta function here with a negative I sign. So the Green's function is I times the Feynman propagator and can be used to generate more solutions if we have inhomogeneous equations, because we can also say that it is the inverse of the differential operator responsible for free propagation. It describes how a particle freely moves when no other forces act on it. So to summarize, we found how particles propagate, which functions describe their propagation, which namely this complex propagating function, and what we also learned, which is a deep insight, that causality requires the existence of particles and to each particle the existence of an antiparticle with an opposite charge, and in fact that we discovered the first antiparticle in 1932, and since then many others.